So we've got one really super important equation that's kind of the daddy of all equations. It comes from just a basic triangle. So if we have this triangle here, and we've got an angle theta that describes the angle that's from this side length to the radius of this triangle, that's really going to tell us a lot of information and help us derive what you're used to seeing as the unit circle. So for this one, let's just consider this circle here. Just this quarter of the circle is all we really need. What we're going to look at is we're going to see if we call this the radius r, and we consider the distance from here to this point. If we know that this is the x-axis and this is the y-axis, we can call this distance here just some x value. And then we can call this distance here, which correlates to here on this line, we can call that some y value, which we can also write here. And so now we have a relationship of three sides and an angle. So the most important thing you need to remember from, I'm sure this was probably from geometry, but definitely from trigonometry, is you're going to have the square of this side plus the square of this side is actually equal to the square of your long side, which is your hypotenuse. Now, if we consider real quick that we don't really like having squares as our final, that's where we get a relationship that I think we're all pretty familiar with, where you square root the sum of squares of your other sides. And so this will tell you your hypotenuse, which I've labeled r, just as a matter of convenience. So let's go back to this first equation we wrote real quick, and let's consider if we turn these x's and y's into parameterized versions so we can talk about these in polar form. Which, remember, if we're in Cartesian and we want to go to polar, we need to get r's and thetas. So if we think about our SOHCAHTOA from back in geometry or trigonometry, whatever you took, that is a description of a few trigonometric ratios and their relationship to an angle. So we know that this is our sine function, and it is the opposite over the hypotenuse, and then our cosine is our adjacent over hypotenuse, and our tangent is our opposite over adjacent, right? So these ratios plus our parent formula here should give us a lot of information about trig that's going to be super helpful for really the majority of our math career. So let's start by looking at this triangle again and saying, okay, well, what is my sine? So if I have sine of theta, right, I know the opposite over hypotenuse is what that's going to equal. So my opposite of theta is going to be y, and my hypotenuse in this case is r. Okay, well, let's do the same thing for cosine, and that's going to be the adjacent, which is our x, over, again, r, since that's still our hypotenuse. And then we'll go ahead and define tangent, but we're not going to really use that right this moment. We'll use it, I mean, probably not today, honestly. We'll use it on a different day, most likely. But we'll go ahead and define it real quick. So if we have our opposite, that's y, over our adjacent, that's x. So we have y over x. So these are the three that you'll really need to be able to manipulate in order to translate into polar. But what we're really going to focus on is these first two. So if we consider sine and cosine, and we have this ratio with y over r and x over r, well, let's just multiply that r over. So now we have y equals r sine theta, and now we have x equals r cosine theta, right? So these are really useful because now we can plug them in up here. So let's go back to our x squared and our y squared with our new y and x functions that we've just created as a translation. We're going to just literally plug these in. So we have our cosine of theta squared plus our sine of theta squared is still equal to r squared. We know that's true. So now we're just going to do a little bit of algebra to multiply all this out. Remember, your powers distribute when you have multiplication. So we're going to have r squared and then cosine squared of theta plus r squared sine squared of theta is equal to r squared. There's one other important one we have to always remember, and that's that sine squared of theta plus cosine squared of theta is equal to 1. Okay? So if we remember that and we look at this, there's a little bit of algebra we can do here to simplify this out. So we can actually factor this r squared out of these two terms. And so we have r squared times, now we have cosine squared theta plus sine squared theta, which is really convenient because now we know, or we remember, that that equals 1. So now if this inside is just going to go to 1, that means we have r squared is equal to r squared, which we know. Let's look at, I'm not going to do the proof for this, just because it does take a little bit of time, but the proof behind this formula is really interesting. So if we have cosine of a plus b, that's going to become cosine of a times cosine of b plus sine of a and sine of b, right? That's one of those ones that I do have memorized because I have done it so much, but the proof behind this is interesting. It's just based on a couple of triangles interlaced in a particular order. Khan Academy has a phenomenal video on it. If you ever want to look it up, just look up angle addition proof and you'll find it. But in the meantime, let's go back to this. So this one, as it looks right now, is not particularly useful for us, but we can turn it into something really useful if we just say, well, let's let b equal a. And it doesn't matter which one you change, it's the same thing. We're going to go ahead and just change it to a though. So we're going to have a plus a is 2a, and I'm hoping that's starting to look a little familiar, because now we have cosine of a times cosine of a plus sine of a times sine of a. And this should be, I'm so sorry, that should be a subtraction sign. I'm getting ahead of myself and thinking of angle subtraction, not angle addition. So this cosine of a times cosine of a is the same as cosine squared of a, and sine a is the same as sine squared a. And now we have something we can play with even more and do more interesting things with. I'm sure you've been surprised before by a question where suddenly they changed into cosine 2a and you didn't really understand how or why. We're going to use this guy and this guy together and figure out 3 other equations that come out of this. So if we look here, we have cosine squared of a, sine squared of a, and then this cosine 2a we're not really going to be able to do a whole lot with. So let's say we want to get this all in terms of cosine squared of a. So all we have to do is subtract this cosine, or the sine squared of a over, so we'll get cosine squared of a, or we'll use, I'm going to change all of this to theta when I do this next one just to keep my life a little easier. So now that's, we're subtracting the sine over, so we have 1 minus sine squared of theta. So now here I have cosine, like I said, I'm going to change to thetas just to be consistent. So this cosine is what we're changing out. We're going to change that out for 1 minus sine. Right, so it's 1 minus sine squared of theta, and then this minus sine squared of theta stays. Okay, so then you can see those just combine. So you have 1 minus 2 sine squared of theta is equal to cosine of 2 theta. Now what we can do is we can actually algebraically move all this stuff over if we want to isolate sine squared by itself. So what we can do is we can subtract 1 over, and then we can divide by -2, or we can flip a bunch of stuff around. I'm going to kind of do it all in one step. So we're going to have sine squared of theta. So I'm subtracting 1 over and dividing by -2. So the 1 is going to become positive and the cosine is going to become negative. And that's all divided by 2. And so that's where that formula comes from. If you have seen that before, I'm sure you have. So you've probably seen this before, and this before, and this before, and this before, and they all come just from this one combined with this one so far. Okay, so the next one we can do is we can go back to this formula here with cosine 2a and the cosine squared and the sine squared, and instead of subbing cosine out, we can sub out sine. So we're going to solve this original parent equation up here for sine instead of for cosine. So sine's going to stay right where it is, and then we're going to have 1 minus cosine squared of theta. And now what we can do is the same thing we did here. So for every sine squared theta we see, we're just going to substitute this in. And this is where people make mistakes. You have to make sure to use your parentheses or this won't work. So I'm going to go ahead and write this over here, but we have cosine of 2 theta equals, and then the cosine is going to stay the same here, so we have cosine of squared of theta, and that's subtracted by, I'll use a bracket just so I don't get distracted on what I'm doing, and then I'm plugging in this 1 minus cosine squared of theta, right? Same thing we did here with sine, just on the other side of the subtraction. And so now we can just solve this out real quick. So we get cosine minus 1, and then minus minus is plus, so we get 2 cosine squared of theta minus 1. Same as we did with sine, we're going to add the 1 over and divide by 2, so we get cosine of 2 theta plus 1 over 2. And that marker is dying. We're going to change him out. I guess I'll finish writing this, is equal to cosine squared of theta, right? So now we have another equation we can use to substitute things out. So we've done a lot of trig here just from two equations. I think that's all of the important ones that I can think of from this equation. So the only other equation we need to remember, which again, there's a proof that you can find on Khan Academy, that's a very good proof. It's not terribly difficult, but it's a little out of the scope for what I want to do today. So we have sine of a plus b, which is going to be sine of one of them times cosine of the other, and then added to sine of the other times cosine of the first. It doesn't matter if you want to do a or b first here, you just have to make sure to get the opposites. So same, your sines need to flip on the other side of the plus, and your cosine and sine need to be opposite as well. So sine a cosine b, or sine b cosine a, and they need to be opposite on the other side of the plus sign. Now if we do the same thing where we are going to let b equal a, now we can say sine of 2a is equal to 2 sine a cosine a. And that's because this turns into an a and that turns into an a, and now they're the exact same. So the next thing we're going to work on is our unit circle. So our unit circle comes from two special triangles. There's two ways to remember this. So I'll draw my two special triangles, and then I'm going to draw my quarter of a circle. And that's not my worst one ever, so we'll take it. So we always start here at the x-axis as our 0 angle. And then if we recall, one full rotation around is going to be 2 pi. And that's actually by definition because that's 2 pi radians, and radian is actually a measure of the radius by the arc length. So it's just something interesting to understand about why we call it radian and why it's 2 pi. It's actually where pi comes from. So since our whole circle is 2 pi normally, I guess I'll draw just a little bit more of this so we remember that there's more. So if the whole thing's 2 pi, then half of it's pi, and half of half is pi halves, right? We'll get to the rest of that in a second. But let's go ahead and talk about this, these two special triangles real quick. So we have, here is going to be our isosceles triangle, right? Two sides equal, and when two sides are equal, that means their angles are also equal. So we have equal angles here. And we know this is 90, so if we have two equal angles and we have 180 total degrees plus 2x equals 0, we can solve this out real quick and we get that x is equal to negative 180 over 2. Negative doesn't really matter in this case. So we'll just get that x is equal to 90. That should be different. Oh, sorry, this should equal 180. That's what I did wrong. And this should be 90. I haven't done this in a while. Okay, anyways, 90 degrees plus 2x is equal to 180 degrees. Because this is a 90-degree angle, the whole thing inside should be 180. So you get 2x is equal to 90. X is therefore equal to 45 degrees. And then if you want to use math to change this into radians, I'm fairly certain you do pi over 180. Yep, that works. 45 divided by 180 turns into 1/4, so you get pi fourths. Right? So now we know that these angles are pi fourths, and that actually makes a lot of sense to us, I hope. So if we already know that these two sides are the same, and then by definition the unit circle has a length of 1, so that actually gives us our coordinates at the two axes. So we have 1 and 0 here, and we have 0 and 1 at pi over 2. So if we already know that the radius is 1, and we're talking about this guy right here, so we'll call him a triangle for now, and then this is our radius. Well, we know the radius has to be 1, which is our hypotenuse. And so now we know that these other two sides, squared and added, have to equal that. So we know that r squared is equal to, let's call this x and y, so x squared plus y squared. In this case, they're the same. So now we have 1 over 2 is equal, right? Because I guess I should write this out more explicitly and not skip some of these steps. So we have 1 is equal to, we're going to just change these to be the same since they're the same. So now we have x squared plus x squared is 2x squared. And now we can divide that over, so we have 1 over 2 is equal to x squared. And then x, when you square root everything, is plus or minus square root of 1 over 2. Now recall, with your square roots, they actually distribute across multiplication and division because they're still powers. It's a power of 1/2. So we can take the square root of 1 just by itself, and then we have the square root of 2 left. So now we have x is equal to 1 over square root of 2. Now we don't like to leave fractions like this, so we're going to rationalize by multiplying top and bottom by root 2. I'm going a little quick through this because I'm hoping this is just review for most of us. I just want to explain where these numbers come from. Root 2 on top, and then regular 2 on bottom. Okay, so now we know that x is equal to plus or minus root 2 over 2. In this case, since we're going in polar, the plus or minus doesn't matter, right? So now we know that this equals root 2 over 2, and this equals root 2 over 2. Now let's recall that we said earlier that our cosine of theta was equal to x, and our r sine of theta was equal to y. So if I have y here, I know my r is 1, so that's easy. So I already know that my sine is going to be my y. So sine must be root 2 of 2. And then you can do the same thing with cosine here. So cosine is root 2 over 2. So this pi fourths angle has a cosine component of root 2 over 2 and a sine component of root 2 over 2. Okay? Just going to clean this up a little bit. And I'm going to teach a trick to get there here in a second to kind of remember your unit circle a little easier. Just want to kind of do the derivations just to do them, both for me and for anyone who might be watching. Okay. So is 1, and so if I have the square root of 2 squared, which is our hypotenuse, minus 1 squared, that gives me the square root of 4 minus 1 is 3, which is this last side. That's the important part of this. So you get a 1, 2, 3 on this triangle. That's where I was trying to go. Okay, so I guess this one isn't double this one. That's maybe where I made my mistake. Okay, so with that being said, now we can get our relationships for this pi over 6 and this pi over 3. So we want cosine of pi over 6. That's going to be the adjacent over the hypotenuse, right? So that's root 3 over 2. And then cosine of pi over 3 is going to be adjacent over hypotenuse. That's 1 over 2. And you'll notice something interesting about sine. That if I do sine of pi over 6, well, that's opposite of our hypotenuse. That's 1 over 2. And then if I do sine of pi over 3, that's going to be from here opposite. Sorry. So opposite over hypotenuse. So root 3 over 2. Right? And so that's the rest of our angles. So we can go ahead and draw these on here real quick. And then we remember pi thirds is bigger than pi 6. Don't let the smaller number in the denominator confuse us. So we have pi 6 here, and we have pi thirds here. And then of course cosine is cosine, so cosines are your x's, sines are your y's. So now that we've done it the more rigorous way, I'm going to go through and show you the trick. Because we can now use our values over here on the left to prove our trick. So what we're going to do is we're going to just think to ourselves, okay, I can count backwards from 3, I think. I hope I can. So I'm just going to do that. Close-ish to the side, I'm going to count backwards from 3. So 3, 2, 1. And then, you know what? I want to do it again. So 3, 2, 1, a little further out. Well, I know the Pythagorean theorem has to do with square roots. So why don't I just square root everything? And that's what we're going to do. And then, well, that doesn't really look right. I know I probably need to divide everything by 2. So this is the pattern. You count backwards from 3, count backwards from 3 again, square root everything, divide by 2. And now square root of 1 is just 1. Square root of 1 is just 1. And now we have our values for all of our angles. And if we check them versus what we just calculated, we can see that we're absolutely correct. So the cosine of pi 6 is root 3 over 2, root 3 over 2. The sine of pi 6, 1/2, 1/2. We nailed it. So this trick is definitely something that's super helpful, And then if you need values on these other quadrants, you just have to do a little bit of geometry from your base values and you can figure them out.